have a read of these and try the questions. Pause the video. Okay, so using integers for the widths and lengths, we've got lots of different possibilities for the different rectangles with an area of 48 centimetres squared. So perhaps, for example, we could have, let's see, 4 centimetres by 12 centimetres would be one option. Now, if we were doing it with lengths, we'd need to make sure we put in the units, and the units of area, given those, would be 48 centimetres squared. If we're just writing down the factors, then we obviously don't need units. Now, the different rectangles would be all the different possible pairs of factors that multiply to make 48. So if you try writing it as a list to make sure that you cover all of them, a good idea is just start with 1. So you could have 1 times 48 would be 48, and then 2, yes, 2 times 24 is 48. 3, yes, 3 goes into 4, once remainder 1, so that will be 16, 3's are 48, 4, that's the one I've got an example there, 4 times 12 is 48, 5 doesn't go into 48, 6, 6/8 are 48, 7 doesn't go into 48, 8 is already on the list. Now, if you've been systematic like that, when you get to a number that's already on the list, then you have all of your factors. So the factors of 48 are 1, 2, 3, 4, 6, 8, 12, 16, 24 and 48. Your rectangles could be any of those pairs written in as lengths and widths on the rectangle. Okay, the second question has a rectangle with an area of 8x plus 48 centimetres squared. Now, what you'll see with the values they've given, 2 times 4x plus 24, and if you remember we miss out the times sign in algebra, we would just write it like this, and multiplying that out we'd want 2 times 4x, which is 8x, and then 2 times 24, which is 48. So there we've got 8x plus 48, which is the area that they asked for. So to make other examples, we need the factors of 8x plus 48. Now, this one's going to be a bit more difficult, but if we stick with integers, we'd need numbers that go into 8 and into 48. So for example, we could have 1, and 1 times 8x plus 48 would make 8x plus 48. Now, does 2 go into those? Yes, it does. So we could have 2, and 2 would be multiplied by 4x plus 24. Then 2 times 4x plus 24 would make 8x plus 48. Does 3 go in? Well, 3 doesn't go into 8x. 4 does go into 8x, 2x times, and 4 goes into 48 12 times. 5 doesn't go into 8, 6, 7, 8 does go into 48 and into 8x, so we can have 8 times, and that would be 1x plus 6. So our factors of 8x plus 48 are 1, 2, 4, 8, x plus 6, 2x plus 12, 4x plus 24 and 8x plus 48. So Eva has said that x plus 6 is a factor, and we can see that x plus 6 is a factor, and if we wanted to make it really clear, we could say 8 times x plus 6 is 8x plus 48, and if one thing multiplied by another gives us a product of 8x plus 48, then each of those things is a factor of 8x plus 48. Pause the video and have a go at these questions. So in answering these, it would be a good idea to write some expressions. 49 is a multiple of 7. Well, what could we write? 7 times 7 is 49. Y squared is a multiple of y. We could write y times y is y squared. 8x plus 48x is a multiple of 8x. If we write 8x times 1 plus 6, 8x plus 48 is a multiple of 8, so 8 times x plus 6, and 8x plus 48 is a multiple of 8x, that's 8x times 1 plus, well, it's not possible there. So the 3 here can all be justified by these. 49 is a multiple of 7 because 49 has 7 as a factor. 7 times 7 is 49, means 49 is a multiple of 7. Y squared is a multiple of y, and y is a factor of y squared. Those are both justified by that expression. Y times y is y squared. Similarly, 8x plus 48x is a multiple of 8x. If we take 8x out as a factor, 8x times 1 is 8x, 8x times 6 is 48x, so 8x is a factor. Also 1 plus 6, or 7, is a factor of 8x plus 48x, which seems a bit weird, but if you think about it, 8x plus 48x is actually just 56x. So you can see what we're really saying is that 7 is a factor of 56x. 8 is a factor of 8x plus 48 because 8 times x plus 6 is 8x plus 48. Finally, we've got the one that didn't work. 8x is a factor of 8x, but it's not a factor of 48. So that was the only incorrect statement. Pause the video and have a go at this question. We've got 2 squared multiplied by 3 multiplied by 5 squared. 2 squared means 2 times 2, which is 4, and that's multiplied by 3 and multiplied by 5 squared, which means 5 times 5, which is 25. Now you can multiply numbers in either order. You could do 4 times 3 is 12 and multiply that by 25, which is not too difficult. It's actually easier though just to spot 4 times 25 is 100 and multiply that by 3. So the final answer, whichever way you've done it, the number is 300. Okay, just a reminder of how to do this the other way round. So if you were given the number 300, you could use a factor tree to end up with this prime factorisation. So if you were asked to express 300 as a product of its prime factors, this is what your answer would be. So to get that, you would first divide 300 into any pair of factors. You might think 3 times 100, seems obvious. And then any time you get to a prime factor, you stop. So 3 is a prime. 100 is not prime. 100 is, let's say, 4 times 25. Neither of those are prime. 4 is 2 times 2 and 25 is 5 times 5. And 2 is a prime and 5 is a prime. So you've ended up with 2 times 2 times 5 times 5 times 3. So we've got this expression here. Now it doesn't matter what you choose as your pairs of factors. So for example, if instead of saying 300 is 3 times 100, you thought, oh, I know that 300 is 6 times 50, then that would be fine. 6 is not prime, 6 is 2 times 3, 50 is not prime, 50 is 5 times 10, 10 is not prime, 10 is 2 times 5. We would end up with the same prime factors. When we're writing a number as a product of primes, we tend to do it in increasing order of the primes and use powers. So for example, instead of writing 2 times 2, we write 2 squared. Pause the video and have a go at these questions. Okay, so there's a few things going on here. First of all, the mistake that Dexter's made is that 9 is not a prime. We can decompose 9 into 3 times 3, so we should have had 36 is 2 squared multiplied by 3 squared as a product of prime factors. Now, to write 36 by 24 as a product of prime factors, you could do 36 times 24 is 864, and that in itself is not the easiest of calculations, and then do a prime factor tree for 864. So 864, I would usually, if it's an even number, just go for 2's, because that's a nice easy one to do. So that's 432, which is also even, so that's 216 times 2, and then 216, that's 108 times 2, and then 108 is, I suppose we could keep going with the 2's, 108 is 2 times 54, 54 is 27 times 2, and then 27 is 9 times 3, and 9 is 3 times 3. Now, that does seem to have worked, and if we're careful and take all of those prime factors, we should have our answer there. What have we got? 1, 2, 3, 4, 5 2's multiplied together and 3 3's. So it looks like 2 to the power of 5 times 3 cubed. Ideally, you take a bit more space. But let's look at this other approach. So Dexter says he just needs to draw a prime factor tree for 24. Well, let's do that and see what we get. So 24 is 2 times 12, 12 is 2 times 6, and 6 is 2 times 3. Okay. So what we could say is 36 times 24 is 36, which is 2 squared multiplied by 3 squared, times 24, which is 1, 2, 3, so that's 2 cubed multiplied by 3, and then just group these together. 2 squared times 2 cubed, if we add the powers there, 2 add 3 is 5, that's 2 to the power of 5, and 3 squared times 3, that's like 3 to the 1, 3 squared times 3 is 3 cubed. 2 to the 5 times 3 cubed, same answer either way. I'd say this way was easier. To do these questions, you shouldn't need to draw a new factor tree for each of the values. You can use this result that Mo has already done for us. Pause the video and have a go. So 200 is half of 400, so we'd need to divide this number by 2. Well, if we had 2 to the power of 4, if we divide that by 2, we'd be left with 2 to the power of 3. So 200 is going to be 2 to the power of 3 times 5 squared. Now 50 wouldn't actually take too long to do the factor tree, but 50 is an eighth of 400. So 2 to the power of 4 divided by 8, or divided by 2 cubed, would just be 2. So that would just be 2 times 5 squared. In a similar way, 100 is a quarter of 400, so divide by 2 squared, leaving us with 2 squared times 5 squared. 80, how many 80s in 400? Well, that's the same as the number of 8s in 40, which is 5, so we're dividing by 5. If we divide by one of the 5's there, we're left with 2 to the power of 4 times 5. 16, well, I guess, yes, spot that 400 is 25 16s. It's worth knowing that 2 to the power of 4 itself is just 16, but you could be saying this value divided by 25. 800, so double this, so we need to times it by another 2, so that would be 2 to the power of 5 times 5 squared, and 4,000, that's 10 times bigger, and 10 is 2 times 5. So if we multiply by another 2, that gives us 2 to the 5, and by another 5, that gives us 5 cubed. Here we want to find the lowest common multiple. So that's a number which is a multiple of both numbers in each part, and it's the lowest of those. Now you could do this with a list of multiples. So multiples of 3, we get 3, 6, 9, 12 and so on. Multiples of 15, we get 15, 30, and in fact I should have kept going there. 15 is on both lists. So 15 is the smallest number on both lists. That is the lowest common multiple of 3 and 15. Now the way we write that is LCM and in brackets 3, 15. Looks a bit like coordinates. So the lowest common multiple of 3 and 15 is 15. Now there is another way to do these using the prime factors. So 3 is just 3 and 15 is 3 times 5. Now what we can do is a Venn diagram. So if we say we have 3 in one of these rings and 15 in the other, so 3 and 3 times 5, well they've both got a 3 in them, so we put that in the intersection because it's in 3 and it's in 15. Then the 3 is finished, there's nothing else to go there. The 15, there's this 5 left over. Now whatever numbers you get inside the rings all together, if you multiply those together, so in this case 3 times 5, that will give you the lowest common multiple. Let's try that with one of these, so 100 and 200. So we've got 100 and 200. So we'll have a ring for 100 and a ring for 200. Now 100 is 2 times 2 times 5 times 5. The reason I haven't written it as 2 squared times 5 squared is that it's easier to cross out the values as we place them onto the Venn diagram when it's written like this. So 200 is just 2 times 100, so that's got an extra 2 on it. So 2 times 2 times 2 times 5 times 5, and let's go. So there's a 2 in the intersection, there's another 2. Now this has got another 2 in the 200, but it's not also in the 100. Now I've realised here I should have made my intersection a bit bigger. There we go, cheating a little bit. Okay, and we've got a 5 in both values and another 5 in both values. So the lowest common multiple is made up of these values all multiplied together. So that's 2 times 2 times 2 times 5 times 5. So that's 25 times 8, which is 200. Now admittedly on these ones you could have probably much quicker said multiples of 100, 100, 200 and so on, multiples of 200. Oh, there we go, straight away we've got 200 on both lists. But just to show how this method actually works. Okay, you should have found then the lowest common multiple of 4 and 6 is 12, the smallest number that 4 and 6 both go into. Lowest common multiple of 10 and 25 is 50, of 3 and 8 is 24, and of 8 and 15, that would be 120. Pause the video and have a go at these questions. Now this is where the Venn diagrams I think really help. Let's take 10 and 25 as an example. Now if you were listing the factors of these, there's not too many factors. So 10 would be 1 times 10 2 times 5, 3 and 4 don't go, 5 we've already got. 25 would be 1 times 25, 2, 3, 4 don't go, 5 goes in 5 times, which we've already got, so those are the factors of 25. So the highest common factor would be the highest number that's on both lists, which would be 5. Now in that example, because there's not too many factors, that didn't really take very long. What we could do though is use the Venn diagram, and in particular what we're interested in will be what's in the intersection, because it will be a factor of both numbers. So if we've got 10 and 25, 10 is 2 times 5 and 25 is 5 times 5, so there's a 5 in common which can go in the intersection. The 10 has the 2 left over, the 25 has the 5 left over, but it's the number in the intersection which is the highest common factor. So highest common factor of 10 and 25 is 5, and the way we'd write that, similar to with lowest common multiple, HCF 10, 25 equals 5. So highest common factor of 3 and 15 is 3. Of 150 and 200, the highest number that goes into both of those is 50. Of 4 and 6, it's 2. Of 3 and 8, they have no common factors, so there is no highest common factor. 36 and 60, here's a nice example where I think it would be worth perhaps doing the factor tree, although yeah, arguably none of these numbers are too tricky, but let's do it anyway. So 6 is 2 times 3, 10 is 2 times 5, 36 is 6 squared, which is 2 times 3 times 2 times 3. So our prime factors, 36 is 2 times 3 times 2 times 3, and 60 is 2 times 3 times 2 times 5. So if we put those onto a Venn diagram, this time I'll make sure it's got a nice big overlap. We have got a ring for 36 and one for 60. So filling in those values, there's a 2 on both lists, there's another 2 on both lists, there's a 3 on both lists, then there's a 3 left over in 36 and a 5 left over in 60, but the key thing is here 2 times 2 times 3, so 2 2s are 4 times 3 is 12, so the highest common factor of 36 and 60 is 12. Now if you were to do that with a list of factors, when you're doing 36 you would have 1 times 36, 2 times 18, 3 times 12, 4 times 9, 5 doesn't go, 6, so you're getting quite a long list. So it may well be that it's quicker to do the Venn diagram method. Can you see how this relates to what we've just been doing? Pause the video and have a go. So we need to make some sandwiches, and each bread roll needs to have an egg in it, but the bread rolls come in packs of 8 and the eggs come in boxes of 1 dozen, which is 12. So we need to know, if we want none left over, how many of each product we need. If we just bought 1 pack of rolls and 1 pack of eggs, then we would have 4 eggs left over. So what we're looking for is a number that 8 goes into and 12 goes into, and we want the smallest number that they both go into. So smallest, lowest, number that they go into, multiple. So we're just looking for the lowest common multiple of 8 and 12. Now you can use the Venn diagram method, you can use writing out the multiples. Personally, if it's a relatively small pair of numbers like these, I would just go ahead and write out the multiples. So multiples of 12, we have got 12, 24, 36. Let's just check where we're at with multiples of 8. We've got 8, 16, 24. There we go, we've got it already, 24. So we're going to make 24 sandwiches, but that doesn't mean the answer is 24. You need to be careful to read the question carefully. What is the least number of boxes of eggs and packs of bread rolls that Rosie needs to buy so she has no ingredients left over? Well, to make 24 sandwiches, how many boxes of eggs is that? Well, the eggs are in boxes of 12, so that's 2 boxes of eggs to make 24 sandwiches. And how many packs of rolls? How many packs of 8 in 24? Well, 3 8s are 24, so that's 3 packs of bread rolls. And that's going to be our answer to the question. Always make sure, especially with slightly longer questions, that you don't just stop when you think, oh, brilliant, I've got there, because it'd be tempting to stop at 24. Thinking about units often helps. If you got to 24 and thought, what are the units? Well, 24 is the number of sandwiches. And then check, did the question ask for the number of sandwiches? No, it didn't. That'll help you just make sure you get the right answers. Last bit here, so lowest common multiple and highest common factor if you have 3 values, for example 10, 15 and 30. So you could write lists, so a list of multiples of 10, of 15 and of 30. So multiples of 10, we've got 10, 20, 30 and so on. Multiples of 15, we've got 15, 30, well, we've already got 30 there, so 30 is a multiple of all 3, and it's the smallest number which is a multiple of all 3. So the lowest common multiple of 10, 15 and 30 is 30. And then highest common factor, you could draw out the factors of all 3 numbers and you'd be looking to see which numbers goes into all of them. Now, you might be able to do ones when they're relatively small like this in your head, because you might spot that they're all multiples of 5. Is there anything bigger than 5 that's going to go into them? Well, 10 has got 10 in it, but 10 doesn't go into 15, and there's nothing bigger than 5 that goes into 10. So actually 5 is going to be the highest common factor of those 3 numbers. Now, just to show, you can do 3 numbers on a Venn diagram. So you need to have a nice big diagram like this. So we've got 10, 15 and 30. So 10 is 2 times 5 when it's got its prime factors. 15 is 3 times 5 and 30 is 2 times 3 times 5. Okay, is there anything that is on all 3 lists? So 2 and not in there, so that's not. 5 is, oh yes, 5 is on all 3 lists. So there's 5, and that is our highest common factor in the middle there. What else have we got left over then? Let me just cross out those 5s. So there's a 2 which is also in 10 and in 30. So in 10 and in 30 we can put the 2 in there. So that's those 2's taken care of. And there's a 3 which is in 15 and in 30. So the 3 can go in there. And then the lowest common multiple is made up of 2 times 5 times 3, which is 30. One last quick thing, just to point out that factors are integers, so factors are whole numbers. Now that means that when we might have said before, because 3 times 7 is 21, 3 is a factor of 21, and 7 is a factor of 21. Well, you could say a half times 6 is 3, which is true, but that doesn't mean that half is a factor of 3 or 6 is a factor of 3. Likewise with the algebraic expressions, now I suppose x plus 3 is not necessarily an integer, but it needs to be an integer multiple of x plus an integer. So 2 times x plus 3 is 2x plus 6, so we could say 2 is a factor of 2x plus 6, or x plus 3 is a factor of 2x plus 6. Third times 9x minus 12 is 3x minus 4, but we can't say that a third is a factor of 3x minus 4, or that 9x minus 12 is a factor of 3x minus 4.